Hello, welcome back to Decaf-Math ASMR, and a warm welcome to you, if you are new here. I hope that you are having a nice start to the new year, but if things aren't going as you had hoped or planned, I want you to know that I am very happy to have you here with me, right here and right now, right here and right now. And I'm happy to be here with you. I have faith and confidence that things will get better, and step by step, you will take care of what you need. Speaking of step by step, today let's have some fun and relax with the idea of substitution. Substitution in the context of algebra and solving systems of equations. So today we'll just build some intuition behind this concept, and of course down the line we can do lots and lots of practice together. But just sit back and relax. Even if you don't really care for the math, it's okay. You can just close your eyes and relax. So just take away what you want or need out of this. I do hope that you find it interesting, or at least thank you for humoring me as I play around with this stuff. So let's start with an example. 3x plus 4y equals 19. 19 equals 19. This is an equation. An equation because there's an equal sign right there, an equal sign. So this is like a mathematical sentence, right? 3x plus 4y equals 19. And x minus 3y equals 2. So there's that equal sign again. So x minus 3y equals 2. So we now have two equations, and together we have a system of equations. So that might be a word or phrase that you'll hear when studying this. I'm just trying to use some words of association here. So together we have a system of equations, and in this case we have two variables that we are solving for. We have x and y, and here we have an x and y, the same x's and y's. So two variables, 1, 2. So x and y are our variables. And so in this case, they are basically placeholders for unknown values. So x has a value and y has a value, but we don't know what they are. And that's what we're looking for. So for this kind of thing, it's like solving a puzzle. Okay, we want to solve these two at the same time. So what's the question? Well, let's take this first equation. 3x in algebra, when you have a number and a letter or variable together, smushed together with nothing in between, it means multiplication. Multiplication, okay? Very good job. So 3 times x plus 4 times y. So whatever value x has, I'm going to multiply it by 3. And whatever value y has, I'm going to multiply it by 4. And then I add those products together and I should get 19. I'm hoping to get 19. So why do we multiply first? Good question. The order of operations tells us that we multiply before we add or subtract. So we do 3 times my first number and 4 times my second number, and then I add, and that should give me 19. At the same time, since this is a system of equations, I also want that first number, just x alone, nothing, times it, maybe just a 1 times itself, and 1 times anything is itself. So the first number minus 3 times the second, again, the multiplication first, should give me 2. So I'm looking for a value of x and a value of y such that both of these situations are true. So in this case, our system of equations has 2 equations, sometimes there's more, and 2 variables, and sometimes there's more, okay? So that's what we're looking for. Now, why do we need substitution? Substitution is just one rule that we can use, or a trick that we can use. It's not the only way to solve this, but it can be very helpful. And the reason we want some kind of trick, like why do we even need a rule? Well, if we look at just the first equation here by itself, 3x plus 4y equals 19. That alone actually has infinitely many x's and y values, possible x's and y values that satisfy this. 3 times some number plus 4 times another number gives me 19. If you have learned this before at some point, you might recognize that you can rearrange this to have the form y equals mx plus b, which is a line. And so this is actually a relationship between y and x. So if you haven't learned this, don't worry about it at all. To convince you that there are infinitely many possible x's and y's, though, for just this first equation, if I were to pick x as 0, I would get 3 times 0 is 0, so that goes away, and then I would basically solve for y equals 19. To move this 4 over, I divide by 4 on both sides, so y equals 19 over 4. So 0 for x and 19 over 4 for y is an example of a pair that works for this first equation. If you plug those values in, you will get that it indeed is 19. But if I set x equals 1, then 3 times 1 is 3, plus 4y equals 19, and just doing a little bit of the algebra, I would get y is 4. And so 1 and 4 are also values, valid values for x and y that also satisfy this. And no one says that x and y have to be integers. They can be fractions, roots, whatever else, okay? So in that case, there are infinitely many pairs. Similarly, the second equation also has infinitely many x's and y values, just two numbers, such that the first minus 3 times the second is 2. So if this has infinitely many solutions and this has infinitely many solutions, how are we going to find just the right pair that satisfies both of them at the same time? So we don't want to guess and check all day. You might not even ever get there, right? So we want to have some kind of logical way to look at this. Okay, and here we go. Here's the substitution. So this is the big picture idea. Each of these equations give us a relationship between x and y. Whatever my first value is, minus 3 times my second, should give me 2. That means I can't just arbitrarily pick a number for x. Let's say the square root of 5. Of course, I would pick something random like that. And then y is 100. That doesn't work. I can't just pick random numbers. They have a relationship. So I'm going to take one of the two equations. It does not matter which one, but I'm going to take one of them and solve for one variable in terms of the other. So it does not matter if you want to solve x in terms of y or y in terms of x, but you do that, and then because it is equal, so you're solving, it's almost like getting an expression of a different variable. So let's say we're solving x in terms of y. I'm rewriting x in terms of stuff that only has to do with y. That way I can plug in or substitute that expression in place of the x in the other equation. So we extract information from one equation and substitute that into the other so that we basically eliminate one of the variables. And we'll use one equation with one variable at that point to solve for one of them, and then plug back in to solve the other. Okay? Sounds like a mouthful, but let's get a concrete idea of what's happening here, okay? So, like I said, it does not matter which equation you start with, but sometimes it is easier to pick one over the other, because in this case, there is no coefficient in front of the x. There's like a little secret 1, because 1 times anything is itself, so 1 times x will be x. And because of that, if I solve for x in terms of y, I won't have to do a division step. I won't need to work as hard to solve for x on one side and y stuff on the other. So because of that, I am going to go ahead and start with this second equation first. You can do the other one, but you'll involve some fractions and maybe it's unnecessarily complicated, but it does work, okay? But let's go ahead and start with the simpler way. So x minus 3y equals 2. So I'm going to solve this using the techniques we've already talked about. If you need to review, just let me know. But basically, I am going to move this minus 3y over to the other side, because I want x in terms of y. So in order to move, this is a minus 3y, so essentially I add 3y to both sides so that this goes away. When I move to the other side of the equal sign, I change the minus to a plus. And if it's a plus, when I move it, it's a minus, right? So when I move it, I get a plus 3y. Good job. my 2 is positive, so plus 2. You could do 2 plus 3y. It's the same thing, right? Because order for addition does not matter, right? So when I move it, it becomes a plus 3y. So I'm still using the techniques that we've talked about and that we will come back and talk about more, okay? So the key thing though is we took this second equation and now I have an expression 3y plus 2 for x. And because of this equal sign, everywhere I see an x, it's literally the same as 3y plus 2, okay? So whatever I do on this side, I must do to this side, because if 2 equals 2, and I add 5 to one side to get 7, I have to do it on the other side, otherwise it's all lopsided, right? So all I did was I moved the minus 3y over here, and this equation is an equivalent equation. It is in terms of information, this is the same information as that second equation. It's just now it has a nice form because whatever my first number is, whatever my x is, I don't know what it is still, but whatever it is, it must equal 3 times the second number plus 2. Okay? So now I have a direct expression (3y plus 2) for x. So now I can plug this back into the first equation. So I extracted what I need from the second equation, and I'm going to plug this into the first one. No need to plug back into the second again, because you will get something redundant like 2 equals 2, because we got this from that. So now we're going to plug this into the other one and see what comes out of that. So everywhere that I have an x, I'm going to put 3y plus 2. So I'm just going to read this across. 3 times, remember times for the times x, and I'm going to put in the 3y plus 2 here. Okay, so just plopping in that x. This is the substitution step. Continuing on, I just leave 4y as is, and then equals 19. Very good. So now you can see that the x disappeared, right? It went away, and now I have 3y plus 2. That's the substitution, okay? And now we have one equation with one variable, now being y, and we can use whatever techniques we know to solve this for y. So let's go ahead and do that. Again, I go ahead and distribute this 3, so 3 times 3y is 9y. Plus 3 times 2 is 6. Plus 4y stays the same. 19 stays the same. 9y plus 6 plus 4y. Well, 9y plus 4y. 9 dogs plus 4 dogs gives me 13 cute little doggies. Yep. 13y plus 6 equals 19. So now do 2 steps to solve for y. We move the minus 6 over, rather plus 6, but to move it over to the other side of the equal sign, you minus 6. So 19 minus 6 is 13 indeed. And then to move this 13 over, you divide. Yes, dividing is the opposite of multiplication. So y equals 13 divided by 13, which is 1. So we have the value of y. Let's see here, don't have much room. Y equals 1. Okay, you ready? Okay, I'm going to go ahead and erase a bit of this. So, y equals 1. So then how do we determine what x is? We want both values, right? Well, we can go ahead and plug in y is 1 into this. X equals 3 times y plus 2. Three times 1 is 3. Very good. Plus 2 is 5. So x equals 5 and y equals 1. Now hopefully those are the two values that we need to solve our original system of equations. So what is really nice about this kind of stuff in algebra is that you can always just plug back in to check. And let's just hope that we have the right stuff, but we can really just check our work by plugging in these values. So let's go ahead and write that out. And I strongly suggest that you plug the two values back into your original equations, because if you plug back into this step, you might have, calculated something wrong or made a mistake between the second equation and this one. So it's nice to check both equations and back to the originals just at the very end, okay? Good. So we have, just making a note, x equals 5 and y equals 1. So let's just go ahead and write out how to check, make sure we understand that, and be clear with which one's x and which one's y. Just because we solved for y first doesn't mean that it's x, right? Y is still y, x is still x. So to check, we have 3 times 5 plus 4 times 1. 3 times 5 is 15. 4 times 1 is 4. 15 plus 4 is indeed 19. Nice. Good job. And then we also want x, which is 5, minus 3 times 1, 3 times y. 3 times 1 is 3. And 5 minus 3 is 2 indeed. Good job. So our two values are correct. X being 5, y being 1. In this case, the numbers are quite nice. I picked them, so I thought so. But sometimes, like I said, the numbers are more complicated. There's nothing that says that they have to be integers, whole numbers, whatever. You might have something with pi's in them. I don't know. It depends on the question. But do note that for these questions, like this question here, we have linear equations because there are no powers to the x's and y's here. Okay, and that's going to be the first set of problems that we practice together. Okay, so I hope that this was helpful, or maybe boring enough for you to be asleep now. Thank you so much for joining me, and I will see you around for a lot more math very soon. If if you are off to sleep now, sweet, sweet, sweet dreams. And if you're about to go about your day, continue on, I hope that you have a very wonderfully blessed rest of